Hello everyone, this is Brockskags, and I'm going to be making this video where we'll look at drawing a shear and bending moment diagram for the very simple statically determinate beam you see before us. And so this is one of a couple videos that I'll make. One video is going to use a free body diagram method, and this is a video that's going to use inspection method. If you're currently attending classes at PSU, generally this inspection method is what I'm calling it, is what's taught in our statics class, so it should look familiar to you. And so you can see the task here, just simply draw the shear and bending moment diagram for it. Really when we draw the diagram, I'm also going to want to write piecewise defined equations, which are going to enable me to know the internal shear force or internal bending moment at any given point x along the length of the beam. One other thing you'll notice, I'm doing everything in variables here, so we'll just consider it a concentrated force F being applied right at the midpoint of the beam, which has some length L, and the midpoint, of course, would be then at L over 2 units away from point A. Also, just in case I forget to say it later on, when I draw beams like this, I generally always consider the origin to be at the very far left-hand side here, where you can see the pin joint is at A, and then the positive x-axis moving off to the right, as is the usual convention there. And so just keeping that in mind. And so our solution method here, if we're going to follow this kind of inspection method, first thing I want to do is figure out the reactions. And so I'll figure out the reactions at A and B. Then I'm going to use those reactions and knowledge about how the forces relate to the internal shear force and how the internal shear force relates to the bending moment to make sketches of the actual diagrams themselves. After that, then we'll basically look at our diagrams, maybe they're constants, maybe they're lines, maybe they're curves, and then come up with the equations to describe those items that we're seeing. So with that being said, let's just hop right into this. And so first off, item 1 is determine reactions here. So grab my pen and get to work. So here we're going to be determining the reactions. And so here we're assuming this beam is in static equilibrium. And so the way I'm going to determine the reactions is by drawing a free body diagram of the entire beam itself here. And so I'll just call free body diagram here. If I want, I can put in parentheses just to make sure I'm clear on what I'm drawing. Is this of the entire beam. And so here that beam, will just use a rectangle to illustrate it. And so there's our beam. As far as the forces we have on it, if I page back up here, we've got the externally applied force F right at the middle. And so I'll go ahead and start with that. And so it's going directly downward here. It's not inclined, so it's moving left and right, but just going straight up and down. And then we've got also to include the reaction forces. And so we've got reaction possibilities here at point A. We say it's a pin joint, so we think, okay, I can split its reaction up into A sub x and A sub y components. And then also we've got a roller over here at point B. And so the roller is only going to be able to generate a reaction force that's perpendicular to the surface that it's rolling on, and so it'll be in the upward reaction since I've got this horizontal force. And so we'll call that B sub y. And so then coming down here to my free body diagram, we'll just plug those in. Here is the A sub x. Here's the A sub y. You can see I'm assuming the A sub y is originally going up and A sub x going to the right. And then here is B sub y here. And I'll change colors, go to blue, just to make sure we remember that this length here is half the overall length, and then I'll go ahead and put half the overall length as well here, since F is right at the midpoint. So that looks like a sound free body diagram. Everything's looking good. And so now we can impose our equilibrium equations on it to determine relationships for how A sub x, A sub y, and B sub y relate to the externally applied force F and the geometry of the beam itself. And so since this is a 2D problem, I've got essentially three equations. I've got the sum of the forces in the x and y directions and the sum of the moments equation, and all those we know have to sum to 0. And so I'll just start off with the sum of the force in the x. So sum of the force in the x, the only thing moving left and right appears to be A sub x, or that not really moving but directed left and right, is A sub x. That's the only one there. I know this has to sum to 0, so that's showing A sub x is going to go to 0. Next, I'm going to go ahead and jump to the sum of the moments equation, just because I've got two unknowns right now, and if I write the vertical equilibrium equation, sum of the forces in the y, I'm going to have two unknowns and I won't be able to solve it at this point. And so I picked point A here for the sum of the moments equation. Really, you're up to point pick whatever point you would like. One of the general things you do is try to pick the point that has the most unknowns about it to eliminate those from our moment equation. In this case, point A right here had a sub x and a sub y. We know a sub x is 0, so now it just has one unknown. B sub y also has one unknown. And so A and B are essentially equally good points in my opinion at this point. So looking at some of the moments about point A, obviously a sub x and a sub y don't go into this equation at all. Their perpendicular distance, if you will, is going to be 0, and so they won't have contributions to the moment equation. Next, if I work left to right, I have f, and it is going vertical. I've got this horizontal distance between it and the point that we're taking the moments about, so it is going to contribute here. In this case, the magnitude will be f times L over 2, but we also have to work about direction. Here you can see it's going to try to cause clockwise motion, and so that'll be negative f times L over 2. You can see here I've got my convention here that I wrote right before my sigma, my summation symbol, that I'm going to consider counterclockwise rotations as positive. And so that's why we have negative f over 2. Finally, the other force that we have to consider on our beam is b sub y here on the far right end. It's going to try to cause counterclockwise rotation due to the direction of b sub y, and it's being on the right hand side of point A. And so we have a positive moment contribution. The force is b sub y. The perpendicular distance, the length, is 2 times L over 2, or just the length. And so we can then set this equal to 0. Here, just a little bit of algebra. One thing we could do is divide everything off by L. That eliminates that. And then isolate b sub y. And we see that b sub y is going to be f over 2. And so now we've related the upward reaction at the roller, b sub y, to the externally applied force. So one more equation to go. We've got the sum of the forces in the y here. And so here we've got a sub y plus b sub y. Those are the two forces going upward, and so we'll take the convention that forces directed upward will be positive, and then minus f is the only one going downward, so we have that, and we know it's in static equilibrium, so we set it equal to 0. Now we're just looking to solve for a sub y. So here, isolating it, a sub y is f minus b sub y. But what was b sub y? Well, that was f over 2, so we can go ahead and substitute that there, and we can see that a sub y is also equal to f over 2. And so this should be fairly intuitive to you. You've got this simply supported beam, right? Pin here, roller here. The force is applied right in the middle, and so it makes intuitive sense that the upward reactions of both A and B would be half the overall load. And essentially all we're doing is showing that explicitly here by drawing the Freebody diagram, writing our equilibrium equations, and seeing the result that A sub y and B sub y are both equal to each other, and they're both equal to the magnitude of f over 2. And so we've now completed step 1, determining the reactions. And so step 2, you can see we're going to make sketches of the shear force and bending moments. And so first thing we need to do is, say, draw the shear force diagram. And so I'll shorten that a little bit and say, well, this is going to be my v of x plot. And so v is just the quantity we're using for internal shear force. X is going to be a position along the length of the beam. Use some one-note magic here in order to quickly draw us some axes here. I'll scoot this around a little bit. Alright, so this will be our internal shear force plot. On the vertical axis, we're going to have the internal shear force, and the horizontal axis will be x, which will be our position along the length of the beam. And so this x equals 0 spot here on the far left is going to correlate with point A here on our actual loading diagram and the far left end of the beam. And so how do we start drawing the shear diagram via inspection, knowing some stuff about the loadings? Well, one thing you know is on the shear diagram is that it's affected by the externally applied forces to the beam itself here. And these externally applied forces could be loads like F here, or they could be reaction forces like A sub y and B sub y are going to be here. And so really there's, in the case of a distributed load, there's a little bit of a integration happening here that we'll talk about in another video. But here we just have concentrated forces. None of them are distributed over a measurable length of the beam. And so here we're just going to have some very discontinuities happening here on our shear diagram. By discontinuities, I mean there's going to be really sudden changes where at a certain point on the beam, the shear diagram is going to go from one value to another value. And so, case in point here, on the very far left end of the beam, Essentially, you can think of the shear diagram starting at 0, but at 0 it's also being hit by this a sub y, which is going to cause an upward reaction force that's immediately going to jump this shear force diagram up to a magnitude equal to a sub y, because we're starting at 0 and then we're hitting a sub y right at the same time, so it jumps up by the magnitude of a sub y, which in our case is just f over 2. And then notice right between A and the midpoint here, the first half of the beam, there's no loads at all on the beam itself here. There's not a distributed load, there's no concentrated forces, and so what that means is that the shear diagram is just not going to change its value at all. And so that's where I can draw just this horizontal line here saying that, hey, between 0 and L over 2, the shear force is going to remain constant. And so then we get over to L over 2, and what happens? Well, we've got a concentrated force here with a magnitude F here. And so what that's going to cause is a sudden change in the shear diagram, a discontinuity, where the shear diagram is all of a sudden going to drop from F over 2 down to actually negative F over 2. And so the amount that it drops here is equal in magnitude to the magnitude of the externally applied force, in this case F. And so we're taking a half an F minus F gets me to a negative F here. And so we've got this sharp drop right here, right at L over 2. But then notice after we get past the midpoint and are walking on the right half of the beam, we have no externally applied forces. So I can just have this thing carry on over till we get to L. At L, what happens? Well, we've got this externally applied force B sub y here, and so we're going to jump right up by the magnitude of B sub y, which is what I have here. And then we get back to the x-axis, which is where we should think we need to be at both the very far left and right ends of the beam itself here. And so this is a plot now of the internal shear force as we walk along the length of the beam. Here I'll kind of skip to step 3 here. Since we're on the shear force, let's go ahead and write the equations of it. And so here we've got a piecewise defined situation here where there's going to be one expression that describes the shear force during the first half, you can see positive F over 2, and another expression that describes the shear force on the second half at negative F over 2. And so the way I'm going to write that is just saying, okay, we've got some V of X here, right, a curly brace here, over one part of the beam it's going to be equal in magnitude to F over 2. On the other part of the beam, it's going to be equal in magnitude to negative F over 2. And so now that we've got the values here, we just have to express the domains as far as where these expressions are good for. And so here I'm just going to write it as inequalities, because we have these disruptions. So we can say 0 is less than x, which is less than L over 2. Essentially this is saying, hey, over the first half of the beam, it's equal to F over 2. And then over the second half of the beam, we would say L over 2 is less than x, which is less than L. And so here we're saying over the second half of the beam, it's equal to negative F over 2. And so this is what we're talking about, the piecewise defined equations to describe the curves, or in this case, the two constants that we're seeing on our shear diagram. And so with that being done, let's go ahead and move to M of X and see how the bending moment is going to change as we walk along the length of the beam. And so our M of X plot here. Same thing, we'll use some one-note functionality here to draw the axes. There we go. And so on this plot now, we're plotting how the internal bending moment M is changing as we walk along the length of the beam. So M is a function of X. And so how do we do this via inspection and knowing the relationships here? Well, the first thing we can look at is, if we go back to our original beam and loading here, there's no concentrated moments that we see anywhere along the length of the beam. And so that means that our diagram's not going to have any sudden changes, sudden disruptions, discontinuities like the shear diagram is having. Also, if we look at the very far left and very far right at points A and B, we've got a pin joint as well as a roller. And so one thing you should know about these reactions is that they cannot support a moment. That's why you can see here when we drew our Freebody diagrams, we just have reaction forces here and not reaction moments. What that tells me is that no matter how the beam acts in the middle, I know that once we get at x equals 0 at point A, it's got to go down to 0. And at x equals L, it's also got to go down to 0 as well. And so that essentially tells me is, hey, at the very beginning here, I'm going to start right at the origin, 0, 0. And so the relationship part of this that we need to know is that there's basically an integration happening between moving from the shear diagram to the bending moment diagram. And so that is the idea here. Actually, I'll go ahead and write that in the margin here. So what I'm thinking is, well, dm dx is equal to v, and so some change in m, if you want to think dm, is v times the change in x, or another way to think of it is m is the integral of v of x dx here. And I'm sure there'll be videos coming where I'll expand upon this idea a lot more. But if I can kind of keep this in the back of my head, I'm saying, hey, the amount that the areas in the shear force, which is what we're saying here, is equal to the changes in the bending moment. And so here we've got two well-defined areas in our shear force plot. You can see the two rectangles forming there. And so one way to think of this is say, hey, I've got some area 1 here and area 2 here. And so the amount that the bending moment is going to change between 0 and L over 2 is equal to this area, area 1, and the amount the bending moment is going to change between L over 2 and L is going to equal to this area 2. And so one way you can start attacking these problems is say, well, area 1 is equal to what? It's a rectangle, so base times height, so F over 2 times L over 2, which is FL over 4. And then we've got the opposite rectangle, so we've got negative F over 2 here. Sign is going to be important for us, times L over 2. So negative FL over 4. And so this is the amount the bending moment is going to change. And so we know if it's starting at 0, and by the time I get to L over 2, I've got to increase by area 1. That means at that point, I've got to be at a magnitude of FL over 4. So I can now plot this point right about here. The next question is, okay, I know 2 points. How do I connect the points? Is it a straight line? Is it a curve? So on and so forth. Here it helps to remember this integration happening here, because here I'm going to be integrating a constant. You can see here f over 2, there's no x in this, and so when I integrate a constant, I'm just going to get a linear function, and this is going to end up being the slope here. And so here I've got a nice line, which is going to connect those points, and so that line is just going between 0, 0 and L over 2, comma FL over 4. And so I've just sketched in the m of x plot between 0 and L over 2, the left half. What about the right half? Well, I'm starting out at a height of L over 4, if you think. I've got to drop over the second half of the beam by area 2. That's negative FL over 4. So I'm going to get back down to the x-axis. And then how do I connect these two known points? Well, it's again integrating a constant to get a linear function, so another straight line there. And so just envision those, instead of having a little bit of squiggle in there, as just perfectly straight lines, nice linear functions. And so now we can just via inspection say, hey, the max moment is FL over 4, which is nice because now if I was trying to do prismatic beam design, sizing, say a rectangular cross section, I knew the need to know the height of it, I could end up using this max moment in order to help me solve for that value. And so now what we only have left is to come up with the equations of these lines. And so here you can use a few different techniques. We do know the ordered pairs, right? Here's L comma 0, this is 0 comma 0 here, and this point is L over 2 comma FL over 4. And so we can then use some equations we know from middle school and so forth, kind of analytic geometry, in order to come up with the equations of the two lines here. One thing you can think of slope is rise over run, or another thing I'm going to be thinking of is this relationship here in red, which basically says, hey, this is the first derivative of m with respect to x. That's also known as the slope, and so the slope of this line is equal to the value of the internal shear force. And so that's what tells me the slope of this line is going to be f over 2, and the slope of this line is going to be negative f over 2 here. You can verify that if you want to by just thinking m is rise over run. Here's one point, here's another point, solve for the slope of this line. Same thing on the left-hand side. So now that I know that, I can at least write the equation for the first line. And so I'll write it right here. My m, let's go ahead and say m is a function of x to emphasize that it is a function, not just a single value. It is going to be piecewise. You can see there's two different expressions going to be relating the two different line segments here. And so the first one, the slope, is f over 2. Here in the back of my head, I'm just thinking y equals mx plus b. And so here's the slope times x. What is the y-intercept? Well, it's right here. It's just right at the origin, so it's plus 0. And then, of course, what is the domain? Well, it's going to be between 0, and I'm going to put less than and equal this time, x, which is less than and equal to L over 2. The reason I'm putting less than and equal on each of these is because the bending moments doesn't have any sharp discontinuities, so I know it's going to go straight into the point 0, 0, and the point L over 2, comma FL over 4. Now for our second relationship, which is the equation of the line over the right half of the beam, at this point all I know is the slope, negative f over 2, times x, but it's not going to have a 0 for the y-intercept, right? You can see this line is going to trace back somewhere up here, and it's going to be above FL over 4. So we'll have to go ahead and figure that out, but first I go ahead and write in the domain, so that's going to be over the left, or excuse me, the right half, so it'll be L over 2 is less than x, which is less than or equal to L here. And so the only things left is to figure out that y-intercept, or vertical intercept on that axis, that's going to go right here. To do that, we need to know one point on this line. And so the point that I'm going to pick out is L over 0. And so here, or I should write known point on M2 of x. And that's the ordered pair L comma 0. And so at this point, we can think of M2 of x as an equation that looks like negative f over 2 times x plus some value, I'll call it c. And so we need to solve for this c value. Well, here I know the one point, so if I plug in a 0 for the left-hand side and a L for the x, that's basically saying, hey, it goes through this point L over 2, or L comma 0, then I can solve for c, and you can see c ends up being here FL over 2. And so this should be our y-intercept then, or vertical intercept. And so here's FL over 2 right there. And let me just move this slightly over. There we go. And I think we have arrived at the required results here. And so if I kind of stop right here and look at the values here, notice we've got this shear force plot. It just has two constant values, and here are the expressions and their domains. And then the internal bending moment here we've discussed, drawn the plot, and we've came up with the equations as well. And so I think that is exactly where we want it to be. One other way you can kind of check yourself a little bit here is if I know this relationship that I've underlined on the right-hand side, is that if I take the derivative of each of these expressions, I better end up at the shear force. And notice that works out for us. F over 2 times x, if I take the derivative with respect to x, I just get f over 2. And then the same thing with our second one, negative f over 2 times x plus FL over 2. If I take the derivative of it with respect to x, FL over 2 is a constant, so it goes to 0, and then the x leaves, and we're just left with negative f over 2, which is going to be the same value that we're seeing in the internal shear force. And so everything looks to be checking out for us. And so thank you for watching the video, and I hope this helps you in tackling your own shear force and bending moment problems. Thank you again.